Okay, physical science folks, it's Dr. Brown who's going to cover some of the issues, key issues in Chapter 8. And these are in some slides that you've already been sent. Some of the key points are the key atomic particles that we'll be describing and discussing are going to be protons, neutrons, and electrons. And we need to know that the protons and neutrons are in the nucleus. The electrons fly around outside the nucleus, statistically in different orbitals that we'll get into later, but they're not fixed orbitals like planets around the sun, but they are statistically generally going to be certain places. Other key points: the protons and neutrons determine the mass. The electrons essentially have no mass or very little mass. Electrons have about 1/1837th or so of the mass of a proton or neutron. And that mass of a proton or neutron is called the atomic mass. One proton weighs 1 AMU. Also, the protons determine the name. The protons are the atomic number of the element, and these are whole numbers. The protons are always associated with a particular name. For instance, in our periodic table, you can't see this very clearly, but say manganese, and you've got a copy of this, and it will be easier to read, but that top number up here is, on manganese, is a 25. So that says that every manganese atom in the whole universe and anywhere has 25 protons. It has more, manganese can have more or less neutrons, and those are different isotopes. The average weight of a manganese, or of manganese in general, is 54.94. So that indicates it has a different number of protons and neutrons, but every atom of manganese will always have 25 protons. The way you determine the number of neutrons is to take, this is the number of protons. The weight is the neutrons plus protons, so you subtract this number from that number to determine how many neutrons magnesium has. And in this case, it looks like if we say on average there are 55 is the weight, and we have 25 protons, so it will have 30 neutrons. I just got that by subtracting this from that. And we can see that on average most manganese have 30 neutrons, but some of them will have more. That's why this is a decimal. This is a weighted weight that tells us what the weight of manganese on average is. Okay. Isotopes, as I said, are different atoms that have different numbers of neutrons and therefore different weights. It's important to know that electrons determine all of the traditional properties and chemical reactions. You know, whether a material would burn in air like gasoline does, whether we can digest it, what color it is, what compounds it forms, everything, all the chemistry we practice in our daily lives by eating, breathing, driving, consuming, cooking, whatever chemistries we practice, we're all dealing with electrons, changes in the electrons, the outer shell of electrons. It's also important to know that if an atom is neutral, meaning no charge, then the number of protons equal the number of electrons. And so back to our periodic table, for instance, back on magnesium, we know it has 25 protons. Every manganese has 25 protons. If that is a neutral manganese, that is also the number of electrons we have. The number of electrons is equal to the number of protons in a neutral atom. Okay. Decay, if we have an unstable nucleus, meaning an unstable number of neutrons and protons in the nucleus, then it's going to seek a more stable configuration, and it'll kick out different particles. Predominantly, the particles that are kicked out are going to be alpha or beta or gamma. The alpha particles have a mass of 4 and a charge of 2, and that's essentially a helium nucleus. Beta particles have a mass of 0 and a charge of -1. That's essentially an electron. Gamma particles have a mass of 0 and a charge of 0. That's essentially pure energy. When an unstable nucleus undergoes decay to get to a more stable configuration, the amount of time statistically taken to decrease the amount of material you have from a certain amount to half that certain amount is called the half-life. So the half-life is the amount of time it takes for, if we have 100 grams of, say, an unstable isotope of uranium, for that 100 grams to become 50 grams of uranium and other materials that we formed, iron and lead and radon gas and helium gas and different gases. I don't know the exact path of degradation depending on what isotope or unstable isotope you have, but the amount of time it takes for half that isotope to disappear is called its half-life. Another key part of this chapter is starting to understand information associated with a particular element. If we have the symbol for an element, and the symbols are taken from the periodic table. For instance, phosphorus is P, sulfur is S. Okay. If you see an element written, and I've written a C here just for a placeholder, it could be carbon, but in the upper left-hand corner, that is the weight, and that whatever number goes right there, since it's the weight, is the combination of neutrons plus protons. That's what the weight is. Again, if back centering on the element, the lower left number is the number of protons, and that's somewhat redundant because whatever the element is, it's always going to have that number of protons. So that's a little redundant because the number of protons defines the element name. But irregardless, that's where the number of protons is put. And the third corner of around our element in the upper right is the charge. If nothing is written there, the charge is 0. And the charge on anything you have a container of, so to speak, is always going to be 0. For instance, elements will always have a 0 charge. If you have a jar of sodium or a jar of chlorine, a container of that, it's going to have a 0 charge. If not, it would shock you. Okay? Any compounds, elements, anything will have a negative charge, a neutral charge with no charge. That'll be a 0, and nothing will be written there. If nothing is written there, that means the charge is 0. The lower right it will indicate the number of atoms. For instance, the molecular formula for water is H2O. And so there'll be a little 2 right there by the H. So if you see H2O, that means 2 atoms of water. And again, on H2O, if we're talking about water, H2O, this 2 means there are 2 hydrogens. When nothing is written, the chemists are basically lazy and don't write things when they don't have to. That means a 1, but you should not write a 1. That's not the proper way. You would leave out a 1. So that means 2. So again, if we have something like anything like a manganese. Manganese might be written something like Mn25 goes down here, and any number, Mn, start again. Manganese is Mn. The number down here will always be 25, and that's because the atomic number of manganese is 25. The number up here could be almost, well, within reason, almost anything. It could be a 56 or whatever. This is the weight, and that is the protons plus the neutrons. So if you see something like that, that would say that this particular atom has 25 protons, and since 56 minus 25 is 31, it's going to have 31 neutrons, because 31 plus 25 equals 56. If you have a charge up here, if nothing is written, that means it's a neutral atom. So if nothing's written, that means it has 25 electrons. But if there's a charge written, for instance, if we have a 2 plus or something written up there, that says that we've lost 2 electrons. There's no longer a balance of electrons and protons. Therefore, instead of having 25 protons and 25 electrons, we've lost 2 electrons, so we would only have 23 electrons. And if there's no number written right here, that means you have one of these atoms. If you have a 2, again, of course that would mean 2. But again, it's important to understand the information that is conveyed when a formula is written. For instance, carbon, here's carbon, has an atomic number of 6 and a weight of 12.01. So a particular carbon atom may be something like 6 with say 14 up here. If we saw that C6, I just wrote a 6 down here in the subscript and a superscript of 14, that would mean that this particular carbon, all carbons actually have 6 protons. This particular carbon would have 14 minus 6, or 8 neutrons. Okay, so if you see this, that says 6 protons and 8 neutrons. Okay, I hope this helps. Please contact me if you have questions. Thanks.